what we were discussing last time. So continuing to Bourgain's principal circular maximum function theorem. And we spent most of the last lecture identifying the enemy scenario. And the enemy scenario is when you have many tangent pairs of circles. Okay. So we're going to grapple with this enemy. So we showed that in that case, you can expect your circles to align themselves in these clamshell configurations drawn here. And we had a technical lemma that illustrates this. So the lemma is saying, suppose we have two circles that are tangent to one fixed circle C0, then if those two circles, which are C1 and C2 here, are also mutually tangent, then the only way this can happen is if the point tangencies are all aligned. Okay, that has to look like this clamshell. So this is a quantified version of that statement. So the tangency is quantified using this delta function, and the alignment of the points of tangency is quantified using this angle function. Yeah. Okay, so this is giving us some information about what our enemies look like, and we're going to try and exploit that to defeat our enemies. Okay. So we're going to begin with a lemma which is going to follow on the heels of this lemma, which says that okay, so there exists an absolute constant of 1, it's bigger than 4, such that under the hypotheses of lemma 1 is this guy here, the following holds. So if we look at the intersection of the delta annulus around C1 with the delta annulus around C2, then this is going to be contained in some annulus around C0, which has width sigma. So here sigma depends on rho, which is separation between the centers of the circles, and kappa, which is measuring the tangency between C1 and C2. Okay. So basically, when we're in this clamshell configuration, all the intersections will lie close to one another, and that allows us to cover them by a single annulus around C0. That's the moral here. You should think, although this lemma is just stated for 3 circles, you should think that there are many different C1 and C2s in some collection that all satisfy this property, and then we're able to uniformly cover their intersections by one single annulus. Okay. Any questions about the statement? Okay, so I'm going to talk a bit about the proof of this thing, which is obviously some kind of geometric argument. It's based on certain bounds for intersections between annuli. So I'm just going to state all the ingredients, which are all proved using trigonometry, and I'll kind of give you some intuition why it's true rather than going through the proofs. So to prove lemma 2, we're going to need this lemma 3. Of intersecting annuli. You can follow up later on. So this tells us that if we have a pair of delta annuli around circles C1 and C2, then their intersection is contained in an arc on C1 of length given by following, so basically square root of the ratio between the tangency and the distance between the centres. However, to stop this from degenerating, it's helping to add some deltas at least. Deltas aren't really doing anything. It's just preventing this from blowing up. C1 equal to C2, for instance. Okay. So basically, it's the ratio between the tangency and the separation between the centres to the 1/2. And there's a second part. Which is that if sigma is bigger than 2 times, well, basically 2 times the tangent which you see between C1 and C2, but again, with the delta, stop things degenerating. Then the intersection, okay, the intersection between C1 delta and C2 sigma contains an arc, a delta neighborhood of an arc. C1 length at least sigma over the distance between the centres to the 1/2. Okay. So I think the easiest thing to do with this lemma is just to draw some pictures of what's going on and explain why it's natural to have this numerology. I'm going to come back later as well, so I'll try to keep copies of them. So first of all, let's look at the first statement. We have 2 circles, C1 and C2. And we're looking at their intersection. So of course, this is, in this case, it's formed by 2 connected components, right? And the lemma is saying that these 2 connected components contain a single arc of the given length. So this would be our arc. Okay, in C1. So in general, this is going to be, kind of over covering the intersection, because the intersections are just these 2 connected components up from the full arc. And this has this length. And I forgot to mention, I would have been started through, in both cases, this is centered at the point of tangents, which is yes. Here is. So remember, omega 1 C1 C2 is the point of tangency. Okay. Does that make sense? So that's the picture for the first part of the lemma. Now the picture for the second part of the lemma is the same, more or less. What I'm going to do here is I'm going to fatten up the neighborhood of C2 up to the sigma, which is going to be larger than delta. And sigma is chosen, so at the beginning of when we do this fattening, it's wider than the scale of the difference between the 2, this difference, which is the tangency. So remember this distance here is by definition the measure of tangency between the 2 circles, which is this delta quantity, and we're choosing sigma to be bigger than delta. So when we fatten up by sigma, we now contain this whole arc of C1. Does that make sense? So a picture for first part is that we've got these 2 connected components that are contained within the arc, and the picture for part 2 is that we fatten up C2, so now we get this whole arc is contained in C1. Make sense? And it's because the sigma is bigger than the delta. Okay. Any questions about this statement? So let's see why it's reasonable to expect these quantities. So I'm just going to go through some examples. I'll just give you some special cases. So the first case, which we'll call the tangent case. I'm going to assume that this delta quantity is small, it's less than delta. And I'm going to assume that the separation between the centers is large. Okay? So in this case, the picture is that we have two circles which are kissing one another. Like this. So we have a single point of intersection for the circles, and when we have the delta neighborhoods, this is the tangents intersection. We expect this to have delta 1.5. Yeah? So, second order problems. This has weight of delta. So in this case, we have a single connected component that forms our arc, that's length delta 1.5. And if we plug that into here, okay, this is about 1, this is about delta, so we get delta 1.5. Yeah? So it agrees in that case. Okay, so we have case 2. Okay, good. So again, I'm going to assume that we're in the tangent case, but I'm going to transition the distance between the centers from being large to being small, multi-delta. Okay, so we're going to start off with the case 1 example. Okay, looking like that. And here the separation between the centers is quite large. And then as we push the centers together, we basically have two copies of the same circle. Okay? So as you can imagine, it's pushing these together, but I have to increase the radii in this guy so they remain tangent. Yeah? So in this case, the length of the intersection is still just one single connected component, and it's going to transition from delta 1.5 to 1. Okay? So we see, for instance, if we plug in if we plug in delta and delta into this ratio, the extreme case we get length 1 when the two circles agree. Okay, so this is kind of interpolating once we fix that we're in a tangent case, it's carrying out this interpolation between these two extremes. Make sense? And then there's a third case, which is transverse case, which is when the delta is about 1, and I'll assume also that the distance between two centers is about 1. Okay, so in this case, the picture's going to look something like this. So the two circles are intersecting transversely, and their intersections will occur on a just delta by delta box. But in particular, these two boxes are really well separated. So here you can see that this length here is about 1. Okay? So if we want to cover these two connected components by a single arc, then we're going to choose an arc length 1. And as you see, when you plug in 1 and 1 into this ratio, we get 1. Okay? So this lemma is interpolated between these three cases, basically. Okay? That's why the numbers come from. Any questions about this? Okay. So then, as I said, the second part, so this is most of it in numerology. The second part, and the numerology in the first part more or less comes from, the second part more or less comes from the first part. So kind of the critical case is when sigma is equal to this delta, and then you see that you get an arc, because the length of this arc is what we're measuring in the first part of the lemma, and then the second part of the lemma, once we factor the sigma, we get this full arc from this picture. So somehow it's the numerology is inherited from the first part. Okay, so I'm just going to assume this lemma 3 and use it to prove lemma 2. So remember, lemma 2 is saying if we have these two circles in our clamshell, then their intersection is going to be contained in the sigma neighborhood of our C naught. Okay, let's see how this goes. Pretty straightforward once we just combine the facts. So what do we know? So from lemma 1, we know we're basically in a clamshell situation. So particularly the angle between horizontal and small, so that's the capital 1 half. Okay. So now we're going to use the first part, lemma 3, which tells us that the intersection that we're interested in, the intersection between the delta neighborhoods of these annuli, that's going to be contained in the delta neighborhood of an arc of length or so then at most the tangency between C1 and C2 divided by the distance between C1 and C2 also 1/2. But if we look at the hypotheses, remember in lemma 2, we're assuming all the hypotheses of lemma 1, we know that the tangency is bounded by kappa times the distance. Yeah? That's this hypothesis, just the bottom there. Right? So this is going to be bounded by kappa. Make sense? Okay. So and finally, by the triangle inequality, we know that the distance between the center of C1 and C2 was less than 2 rho, because we've controlled the distance between C0 and C1 and C0 and C2. And so, if I look at 2 times the tangency between C1 and C2 plus delta, that's going to be bounded by 2 times tangency between C1 and C2 plus beta, because it's bigger than delta. And then by our hypothesis, this is bounded by kappa times the kappa times the distance between C1 and C2. And then you can apply this boundary bound all by 4 times kappa times rho, which is going to be bounded by A1 times kappa times rho, which is sigma, whenever A1 is totally bigger than 4. Okay? So the point is here that our sigma, our choice of sigma, is going to be bigger than this quantity, which is exactly what we need in order to apply the second part of the lemma. It's big enough that when we fatten up by sigma, we just subsume this whole arc. Okay? So by lemma 3b, or 3 part 2, sorry, we know that the intersection between C1 delta and C0 sigma contains C2 I'll do it this way around. Yeah. Just a second. Okay. We like want C130 here. Okay. Sorry about this. Just a second. So if I have C1, C0, then I think the same thing holds. Because C1, C0, tangency that's bounded by beta, so I can bound that by beta. And then I can probably add this to 3 things. Everything's going to be with delta. Okay. But anyway, so sorry about that. Anyway, this we should be able to sit at line number 3 and see that this contains an R and delta neighborhood of an R of C of length least sigma divided by the distance between C0 and C1, 1/2. And then here we know that sigma is equal to A1 times capital times rho, and the distance is rho. So this is A1 times capital 1/2. Okay, so at this point we've got all the information we need, and okay, and in both cases these arcs are essentially the same point. Well, okay, this arc, sorry, is centered at omega C1, C2. And this arc is centered at omega C1, C0. Okay. Okay, so now we've got all the information we need. So first of all, we know that the angle between these points on C1, where the centers of these arcs are, is small. We know that the length of the arc containing the intersection is small, capital 1/2. But then we know that the intersection between C1 and C0, sigma contains an arc which could be made large, say A1 times capital 1/2. So if you combine these 3 facts together, which is A1 large enough, you can contain this arc in this arc, which is contained in C0. Does that make sense? Clear? Okay. So the important thing is that we make sure that this angle is small, which is the very first condition, so that the center of the arc is close to one another. Okay. Okie dokie. Right, so there's a second geometric lemma that I want to discuss, which is going to be intersecting out line part 2. Okay, so this lemma Again, it's going to be two parts. So for the first part, I'm going to say that the intersection between two delta annuli has at most two connected components. And each has diameter, size, bounded by delta, divided by the square root of the tangency times the square root of the distance. And again, we're going to have deltas to prevent things degenerating. Okay. So as a consequence of this, that we get the volume of the intersection is bounded by delta squared divided by the square root of the tangency times the square root of the distance. Okay. So what this lemma is measuring, going back to our picture here, is the length of these intersections, which is much smaller than the length of the arc containing the intersections typically. Okay. And there's going to be a second part. Which states that if we have a large sigma again, so sigma is again chosen large relative to the tangency between C1 and C2. Then the intersection between C1, the delta arc around C1 and the sigma arc around sigma radius around C2 is bounded by delta times sigma divided by the distance between the centers. Plus delta 1. Okay. So the second part of the lemma is should be fairly obvious from what we've already discussed, because as we've mentioned, once we fatten up C2 to a sigma radius, we contain this whole arc. Okay, and basically, so we had a lower bound of this form from before, and this is just saying that the upper bound also holds. That's that we more or less only contain the arc. Okay, so it's the arc circle from here to here, which will have this length. Okay. So for part A, I'm going to do the same thing and motivate the numerology through the 3 examples. So it's pretty straightforward here. So let's look at the cases that we described before. In case 1, we have the cat well, I could just discuss that a minute if you understand. So in case 1, when we're in a tangent case, where the tangency between C1 and C2 is equal to delta, then we see that we have a single connection component of length delta 1/2. And if we plug in the numbers, well, this is about 1, it's about delta, we get 1/2, delta divided by delta 1/2, delta 1/2, that agrees there. Okay, then we can transition from this case to the case where the 2 circles agree. So that corresponds to shrinking this distance from 1 to delta. So as we do this, this goes from delta 1/2 to 1, because the whole the intersection is the whole circle, so it's length 1. So we get there, so that makes sense. And then case 3 is the transverse case. And here, okay, delta and the distance are about 1, and we see that the length of the intersections in the components is tiny. It's just delta. And indeed, we get delta divided by 1, which is just delta. Okay, and of course, once we've got the length of the component, we just get the volume of the intersection because it's just the length times the width, so it's just delta times the length. Yeah? Does that make sense? Seem reasonable? Okay. Okay. So at this point, I'm going to describe a little bit about the proof strategy for completing the proof of the circular maximal theorem. So now we have basically all the prerequisite geometric ingredients, okay? So we're going to try and remind ourselves of what the goal was in the way we reformulated the problem. Well, I'm always to show the following proposition, which is the dual form circular maximal theorem. Okay, so remember the circular maximal theorem is trying to prove that circular maximal function is bound for p bigger than 2. So the dual form will want to be p between 1 and 2. Okay? So I'm going to work for all p between 1 and 2 in range that exists from quantity epsilon p bigger than 0, which is the following goals. So if we look at our multiplicity function, that's the sum of these oscillating characteristic functions of delta annualized, and we measure this in the LP model, then we want to be able to bound this by the cardinality of the set of circles raised to the power of 1 over p. Times delta factor, which is delta 2 over p minus 1 plus epsilon p. Okay? So remember, getting this epsilon p is crucial because this allows us to sum in the frequencies. Okay, so we need some positive power. That's the dual form we discussed in the first lecture, and that's how that's the things we reduced to showing. So let's remind ourselves what we know. We almost have this.
Jonathan,
Yeah.
did we have some coefficients?
You can put, okay, yeah. So I stated it with coefficients, but this is basically a restricted weak type. And if we get a restricted weak type inequality for all values of p, then we get a strong type inequality by interpolation. So yeah, I dropped the coefficients that we had before. But that's because basically you think the coefficients of 0 to 1 indicate sets, and then do a restricted weak type. Thanks. Any other questions? Okay, so what do we know? So first of all, we have the L2 bound. I'm describing the vertical lectures. The L2 bound is the shape, and it basically corresponds to taking epsilon 2 to equal 0. So it just falls short what we need to get a maximal estimate. And that necessarily falls short. We can't improve the L2 bound. L2 probably fails for this. On the other hand, there's an extremely simple L1 bound. The L1 bound, followed just by finding inequality. So we just found the sum of the L1 norms to these oscillating characteristic functions. So once we do that, kill all the oscillation, and these are basically just characteristic functions of delta annuli. Delta annuli has volume delta, so this is just bounded by delta times the cardinality. Okay, and if we compare that to what we're shooting for, well, when p is 1, we got 2 over 1 minus 1, which is 1. So this is like taking epsilon 1 to get to 0. Okay. So we get the epsilon p equals to 0 at the 2 endpoints, p equals 1 and p equals 2. So we can interpolate. Yes, here we're just using the log convexity of the norms for interpolation. Fancy. we get it from all values of P. We have the design inequality, but we just miss out by by having a zero value of epsilon rather than positive. Okay. So we're tantalizingly close. Okay, we've already seen this more or less. We're very close to proving the inequality. We're just going to gain this epsilon by one way or another. Okay, so how are we going to gain the epsilon? Well, the strategy is going to be the following. Together, we'll glory this whole. So we're going to decompose our given set of circles into two parts. So we're going to have C is going to be decomposed as union of what I call C trans, which is going to be a collection of transversely interacting circles, and C tang, which is going to be a collection of tangentially interacting circles. And we're going to prove some refined bounds, taking into account the special structure of these subcollections. So for the transverse circle, we're going to look at our two band, and we're going to get down to improvement over our bound above. And we've already seen this more or less. So see this one, 3A. So okay, so if we compare for a 3A with an improvement by delta epsilon, we've already seen this. We've seen an example where we had certain collection of circles that doesn't have too many tangent pairs, then we've got an improvement. So this is the same thing here. Okay. So then we're left with the tangent guys. The goal here is going to be to prove an L1, get an L1 improvement. We're going to look at the L1 norm, and we're going to shoot for an inequality of this form. So we're bound this by delta 1 plus epsilon times the kind of C. For B. If we compare 4B to 3B, this is improving over 3B by delta the epsilon, and the only way we can get this improvement is by exploiting the fact that we've got this special geometry of this circle collection of C tang. Okay? So we more or less know how to get 4A. So the question is, how on earth are we going to get 4B? Where's this coming from? Okay? So any questions about this general setup? I'll move on to. Okay, so just to map things out clearly, the ones we've shown 4A and 4B, we'll interpolate and 4A with 3B, so the improved L2 for the trans with the L1 for any arbitrary set, and we'll also interpolate 4B with 3A, that's the improved L1 for the tang with the regular L2 for anything, and then for both, for both subfamilies, we'll have improved LP bounds for all P. Then we're in a good state. And this interpolation, so of course we're using our function here, which is the collection of circles. It's important we just use log convexity of the norms. We don't use any kind of interpolate because we have to exploit the special properties to it. Okay, so that's the strategy. Does this make sense in broad terms of strategy? Any questions about this?
How can you get the gain from the tangent?
Yes, so I'm going to discuss that at the end. Anything else? Okay, so let's try and see how we get the gain from the tangent, which is going to be basically what we did last lecture. But I'm going to sketch out the idea here. Forward. So to reiterate, we've already seen the improved L2 bound in the transverse case. Now let's turn to the tangent case with y is 0 and so why do we get into one improvement? Well, tangent. Well, the idea is as follows. So if our collection of C, our collection C tangent has many tangent pairs, we can basically isolate many clamshell configurations within C tangent, and we're basically going to break up C tangent according to these clamshell configurations and treat them one by one. Okay, we're always good to break things up here because we're trying to do now one estimate. Okay, so let's just look at one of these clamshell configurations. So remember, for sigma equals this A1 rho times kappa. So I'm assuming this is a clamshell with these parameters in this lever. So kappa is the angle between all the lines of tangency, and rho is the separation between the centers. So we'll assume we're in a situation like that, which we can do by pigeonholing. So for this sigma given by this parameter, we know that the intersection between the pairs of circles in the across the lever, but we know the intersection between the delta annuli within the clamshell are contained in some single sigma annulus around the circle C naught. Okay, that was one of the things we proved earlier on. We'll get something like that. Okay. So what that tells us is if we go back to an L2 bound, then if I restrict the L2 norm to lie away from this sigma annulus, then this should be favorable. Because whenever we have off-diagonal terms, okay, so remember, we can just expand this as no products. These are oscillating characteristic functions of annuli, but we can just kill the oscillation. Whenever we have off-diagonal terms, these intersections are contained in this guy. We're removing that guy from the domain of integration. So we should only get diagonal terms, and diagonal terms behave well. So this should be favorable. So we should get a good L2 bound away from this C, this annulus, okay? So what that allows us to do is to restrict to what happens on the annulus, okay? And to do that, so now I'm going to look at this multiplicity function, but I'm going to just take a norm over the, and this time an L1 norm, over this sigma annulus. Okay? And we're going to apply the same trivial argument, we'll bound this by the sum the L1 norms. oscillating characteristic functions. We're now killing the oscillation. So this is basically the sum, the intersections between these delta annuli and the sigma annulus. Okay? And we have a volume bound for this. So we can bound this by sigma divided by the distance between C1 and C2 or C1 half. Dilemma. And now we have to think about how we've set things up. Well, we're choosing a clamshell where the step distance is always about rho. And we've chosen a sigma, which is basically what A1 is constant, so rho times kappa. So when we take account of this, there's a missing delta here. When we take account of this, we get delta times kappa to the 1/2 times the kappa to the 1/2. And if we compare this to the trivial L1 bound, which is 3b over there, we see we've gained by kappa to the 1/2. So if we choose kappa to be some power delta, then everything is matched. Okay. So that's where the hell this is all going to tie together. So I'm going to finish early, I guess. So on Friday is the last lecture. We're going to implement this strategy. So there's a lot of things that don't really make too much sense here. Mainly, there's a question about how we perform this decomposition, and then how we truly pass to these individual clamshells. Okay. So, but this is going to be the strategy that we implement. Transverse case, good L2 bound, and then for the tangent guys, we get a good L1 bound by noting that we can localize to delta neighborhood of fixed sigma neighborhood of fixed annulus. Okay, so
Thank you, Jonathan. Any questions, comments, remarks?
there's no more trade-off.
Anyone? All right, so thanks again, and then we have a break.